Beneath Vancouver's calm coastline, a powerful force is awakening. The Pacific Northwest, famed for its beauty, hides a volatile secret just below the surface.
A whole lot of shaking going on. In the last 36 hours, dozens of earthquakes have been recorded.
The Pacific Northwest is no stranger to geological tension, but when the Cascadia Subduction Zone recently slipped without warning, scientists across the globe issued an immediate red alert, an alarm that rattled not only the scientific community, but also raised critical questions about the stability of one of the most dangerous fault lines on Earth. This was not the anticipated megaquake. It wasn't even an event that registered with the kind of thunderous rumble normally associated with subduction zone tremors. Instead, it was silent, stealthy, and insidiously revealing. In one of the most closely monitored tectonic environments in North America, the Cascadia Zone's sudden movement, absent the usual seismic outcry, marked a moment of profound significance. It moved, quietly, and in that eerie quiet, it shouted a warning. Before we start, hit the like and subscribe buttons for more exclusive news. The Cascadia Subduction Zone stretches for over 600 miles, running from Northern California through Oregon and Washington up to British Columbia. It's where the Juan de Fuca plate is being forced beneath the North American plate, a colossal act of geological compression that builds up seismic stress over centuries. Historically, this zone is capable of producing earthquakes on a magnitude similar to the devastating 2004 Indian Ocean quake or the 2011 Tohoku earthquake in Japan. The most famous of Cascadia's past events occurred in the year 1700, a magnitude 9.0 earthquake that sent tsunamis crashing into Japan. Since then, the fault has been unnervingly quiet. Until now. What scientists observed was not the massive, destructive rupture that people in the Pacific Northwest have been warned about for years. Instead, it was a phenomenon known as a slow slip event, a silent, gradual movement of the tectonic plates along the fault line. These events often go unnoticed by people on the surface, but they can release the equivalent energy of a magnitude 6 or greater earthquake over days or even weeks. The alarm this time wasn't because of the event itself, but because it occurred outside of the expected cycle and in a segment of the fault known to be locked and loaded with pent-up strain. In simpler terms, the wrong part of the fault slipped at the wrong time, and it did so without warning. The implications of this unexpected movement are immense. Normally, slow slip events in Cascadia occur deep below the surface, often more than 30 kilometers down. They usually recur on a predictable cycle of around 14 months in the southern portion of the fault, particularly around the region near Puget Sound. But this recent event didn't fit that pattern. It happened higher up, closer to the surface, and it wasn't supposed to happen yet. Scientists detected anomalous shifts in GPS data and strain meters, showing that a portion of the fault had suddenly begun to move in a way that suggested it was freeing itself from the mechanical resistance that holds it together. And the moment a locked segment starts to act irregularly, it triggers fears that the adjacent zones, those still under immense pressure, might be next. This isn't just a regional concern, it's a global red flag. The Cascadia Subduction Zone has long been categorized as a sleeping giant, and part of that label comes from its long recurrence interval. Unlike the San Andreas Fault, which releases energy in more frequent moderate quakes, Cascadia tends to go quiet for centuries, then ruptures in a single cataclysmic event. A sudden and unpredicted slip, especially in a zone that had not previously shown signs of instability, suggests that the fault's stress distribution may be more precarious than anyone previously thought. In essence, the beast stirred, and it wasn't supposed to. One of the most disturbing aspects of this development is that it undermines some of the foundational assumptions scientists have used to model the region's earthquake risk. The traditional thinking has been that slow slip events help relieve stress in the fault and delay the potential for a massive rupture. But if certain segments are slipping without releasing pressure, or worse, are transferring it toward the locked, earthquake-prone areas, it changes the calculus dramatically. It could mean that the system is approaching a critical threshold where even a small perturbation might cascade into a larger rupture. This unpredictability is what makes the red alert so serious. The lack of forewarning means emergency planners, seismologists, and local governments are now operating with less confidence in their models. If slow slips are becoming less predictable, or occurring in regions previously thought stable, it becomes harder to anticipate where and when the next major quake will strike. In a region home to major cities like Portland, Seattle, and Vancouver, this uncertainty is not just academic, it's existential. The science behind these movements is complex and still developing. When tectonic plates grind against each other, the energy doesn't always release in a violent jolt. Instead, some of it dissipates in slow, creeping motions that can only be detected by sensitive instruments. These slow slip events are often accompanied by a phenomenon called tremor, low-frequency seismic noise that isn't felt but can be recorded. However, in this latest slip, the tremor signature was either absent or radically diminished, suggesting a change in the mechanics of the fault. This abnormality has prompted a flurry of new research and reevaluation, as it challenges the idea that tremor is a necessary indicator of deep fault movement. Another layer of concern comes from how this silent slip interacts with hydrological and geological systems on the surface. A shift deep underground can subtly change groundwater pressures, affect volcanic activity, or even influence the structure of sediment layers that can amplify shaking during a future earthquake. Scientists are now urgently reviewing data from volcanic systems in the Cascade Range to determine whether any correlated signals exist, anything that might hint at broader destabilization. There is also growing concern about the cascading consequences of such a slip in terms of landslides and soil liquefaction. The Pacific Northwest is geologically young, with heavily saturated soils and steep terrains. A major rupture in this area could trigger secondary disasters far beyond the shaking itself. The silent nature of the recent slip only underscores how little time there might be to respond when a rupture finally begins. Moreover, this recent shift occurred in a part of the fault where urban development has crept closer to potential danger zones. Infrastructure, from highways to pipelines and power grids, was not designed with this silent hazard in mind. Even without a massive earthquake, gradual shifting can stress bridges, compromise foundations, and subtly distort structures in ways that make them vulnerable to future shaking. The silent slip might not destroy a city overnight, but it sets the stage for catastrophic failure when the real quake comes. From an atmospheric and oceanic perspective, any tectonic movement near the Cascadia margin also raises flags about tsunami generation. Even small displacements on the seafloor can cause shifts in ocean volume. And when the full megathrust finally goes, it is almost certain to generate a tsunami on par with the most destructive in human history. The fact that this slip occurred closer to the surface increases the risk that future motion in the same area could translate into vertical displacement, exactly the kind needed to launch a massive wave across the Pacific. For coastal communities that already live with the ever-present threat of a Cascadia rupture, the warning issued by scientists comes as both a vindication of their long-standing concerns and a sobering recalibration of the threat timeline. The urgency now is not only in preparation, but in developing a new understanding of how and when this fault chooses to move. Public agencies are reevaluating evacuation plans, communication systems, and emergency infrastructure. But preparedness only goes so far when the event in question may strike without any recognizable precursor. There's also the broader psychological impact of this event, how it reshapes the public's sense of security. In an era where climate change dominates disaster planning, seismic threats often take a backseat. Yet, a sudden slip in one of the most dangerous faults in North America is a stark reminder that the planet's internal processes remain every bit as unpredictable and potentially devastating as surface-level weather patterns. This event is a wake-up call not just for geologists, but for everyone living within reach of Cascadia's restless margins. As researchers scramble to refine their models, deploy additional sensors, and reinterpret the vast archive of seismic and GPS data, one thing is clear. This wasn't just a slip, it was a statement. The Earth sent a signal, one that defied expectations and refused to follow the scripts we've written for it. In doing so, it has challenged a generation of seismologists to question what they know and to dig deeper, literally and figuratively, into the hidden dynamics of the Cascadia Subduction Zone. What makes the situation even more urgent is the interplay between tectonic motion and human timing. Civilization in the Pacific Northwest has grown dramatically since the last major rupture in 1700. Today, millions of people live in areas that would be heavily affected by even a partial rupture. Infrastructure spans rivers, cuts through mountain passes, and lines coastlines that would be the first to be hit by a tsunami. The longer the fault remains locked and strained, the greater the eventual release, and the greater the risk to those who live above it. Even without the arrival of a megathrust quake, the consequences of these silent slips can be far-reaching. They test the resilience of transportation corridors, power networks, and water systems. They challenge the foundations of buildings not designed to bend and sway over months. And they reveal, perhaps most unsettlingly, how little we still understand about the inner workings of Earth's crust. Every new piece of data from this recent event peels back another layer of mystery and replaces it with urgency. Perhaps the most profound implication of the red alert is that it forces a change in mindset. The notion that we can anticipate these events based solely on past behavior has been undermined. The Earth does not run on human schedules, nor does it conform to our risk models. This unpredictability demands a more flexible and robust system of surveillance, one that doesn't just track expected signals, but listens for anomalies, for deviations, for whispers in the noise. The recent slip was one such whisper, a subtle signal that the system is still alive, still shifting, and perhaps closer to breaking than previously believed. The Cascadia Subduction Zone's recent silent slip has widened the lens through which geophysicists now view tectonic interactions, not just as isolated regional phenomena, but as part of a larger global network of crustal stress and redistribution. What makes this particular movement so vital to dissect is that it deviates not only from what was anticipated, but from how such events have historically behaved. The very nature of a silent slip occurring in an unexpected location upends previously trusted assumptions, signaling that the system's internal dynamics may be evolving. That evolution, unseen, ongoing, and potentially escalating, demands a rethinking of everything from seismic risk projections to long-term land use policies across the Pacific Northwest. Each fault system on Earth has its own rhythm, a kind of geological heartbeat. For years, Cascadia's beat had appeared regular enough. Quiet, subtle tremors spaced apart by lengthy dormancy, interspersed with occasional slow slip episodes deeper beneath the crust. The recent slip, however, diverged from that metronome. Its profile, shallower, quieter, out of cycle, indicates that the fault may be exhibiting complex nonlinear behaviors. These are not just deviations. They could be the early signs of a transition from a stable regime to one teetering on instability. This possibility introduces cascading layers of concern. One of the chief worries among geologists is the concept of stress loading. When one section of a fault relieves its energy, that energy doesn't just disappear. It can migrate. The redistribution of stress from one area to another is a process still not entirely understood, but it has been observed in several large-scale events globally. If this recent slip has changed the stress field in the upper segments of the fault, especially toward those portions believed to be locked, it may have increased the likelihood of rupture in those neighboring regions. These zones, already under immense tension from centuries of pressure, may now be that much closer to a breaking point. This interconnectedness extends beyond Cascadia's main thrust line. The region is bounded by a complex web of other geological structures, splay faults, strike-slip faults, and volcanic plumbing systems that feed the Cascade Range. When one piece of this puzzle shifts, it exerts influence across its neighbors. A shift near the plate interface might modify pressures feeding a volcano's magma chamber, or distort the stress around adjacent crustal faults. The silent slip's ramifications, then, might not be limited to earthquake risks. They could presage volcanic activity or ground deformation in areas not traditionally seen as high risk. And this interdependence leads to an increasingly pressing issue: the ability of current monitoring systems to provide a complete and actionable picture. While GPS arrays, tiltmeters, and seismometers saturate much of the region, even this dense network wasn't entirely prepared to capture a shallow slip of such subtlety and stealth. The resolution of these instruments, both in time and in space, may simply not be sufficient to detect the earliest signs of transition from slow creep to violent rupture. This is not a failure of technology so much as a call for its advancement. It suggests that future investments must prioritize multimodal detection systems, ones capable of reading the deepest murmurs of tectonic motion and converting those whispers into warnings. There's also the challenge of data interpretation. The complexity of the Earth's interior means that readings can be ambiguous or contradictory. A GPS station might show millimeter-scale movement, while a nearby seismic array remains quiet. Deciphering what these variations mean, especially when they break from established patterns, is a process that requires both massive computational resources and human insight. This recent event has already sparked re-evaluations of machine learning models trained to detect precursory signals. Researchers are now sifting through petabytes of archival data in hopes of identifying previously missed anomalies, faint tremors, hidden distortions, unusual strain patterns that could shed light on what this latest slip truly represents in the long-term evolution of the fault. But even the best technology cannot yet penetrate the opaque veil that separates surface observations from the deep Earth. What lies beneath, kilometers down where rock behaves like both solid and fluid, where heat and pressure blur the rules of classical mechanics, is still largely inferential. Models attempt to recreate these processes, but without direct measurement, there remains a chasm between prediction and certainty. The recent slip, in defying expectations, emphasized just how much remains in that gray area. It challenges researchers to explore not only new modeling techniques, but also to re-examine the fundamental physics that govern fault behavior. This situation has also stirred debate within the scientific community about whether there may be multiple failure modes operating along the Cascadia margin. Traditional earthquake theory suggests a binary. Either the fault is locked in building strain or it ruptures violently, but new ideas propose that there may be intermediate phases, modes where the fault partially gives way, creeping and groaning, but never fully breaking. These semi-coupled phases could last years or even decades, and would be incredibly difficult to distinguish from noise. If Cascadia is currently entering such a phase, it would redefine how scientists interpret surface signals and might drastically alter seismic hazard maps throughout the region. The notion of intermediate fault behavior also dovetails with a growing body of research into aseismic creep, where the fault moves slowly without generating any noticeable tremor or vibration. This kind of motion has been recorded in other subduction zones, like those in New Zealand or Alaska, and may now be underway in Cascadia. If this is the case, then what appeared to be a discrete, anomalous slip may actually be the latest chapter in a slow-burning process that's been unfolding for years. That has enormous implications, not just for earthquake forecasting, but for how cities, towns, and infrastructure systems prepare for long-term deformation. Land deformation is a particularly insidious threat. Unlike a sudden quake, which causes immediate and visible destruction, slow crustal warping can degrade infrastructure in silence. Bridges lose alignment, pipelines bend and fracture, rail lines twist ever so slightly until they derail. This creeping disaster lacks the visual drama of collapsed buildings, but carries a comparable cost in terms of repair and maintenance. Engineers are now being advised to consider not just peak shaking in their designs, but also long-duration, low-rate ground motion as a factor in structural longevity. This slow transformation also alters the hydrology of the region. Groundwater tables can rise or fall, affecting everything from agriculture to municipal water supplies. Shifts in subterranean pressure can force water into new pathways, destabilizing slopes and increasing the likelihood of landslides, especially in the wet, forested hills of western Oregon and Washington. And when these slides occur, they can dam rivers, threaten roads, or trigger secondary flooding disasters. So while the silent slip may seem benign, its after effects can echo far from the fault line itself. Another underappreciated dimension of this event is its potential to influence oceanic systems. A slip along the offshore portions of the Cascadia margin can subtly change the seabed's shape. Even minute displacements can alter ocean currents, sediment flows, or the habitats of deep-sea species. These changes might not be immediately measurable, but they represent another layer of complexity in a world where geological and ecological systems are tightly interwoven. A future in which seabed motion influences fisheries, shipping lanes, or underwater cables is not implausible, and demands foresight from marine planners and oceanographers alike. These transformations are not occurring in a vacuum. They coincide with broader environmental shifts brought on by climate change. As sea levels rise, the margin between land and water becomes more vulnerable to tectonic upheaval. A quake-generated tsunami in a time of higher ocean baselines will penetrate further inland and with greater force. Wetlands that might once have absorbed some of this energy are now eroded or paved over. Coastal defenses, designed based on historical norms, may no longer be sufficient. The risk matrix is compounding, and the recent slip injects an urgent reminder that tectonic risk must be considered alongside climatic risk in any future planning. From a socio-political standpoint, the implications are equally significant. Governments and agencies tasked with public safety must now wrestle with the fact that their primary hazard models may be incomplete. Funding for seismic retrofits, once calibrated to long-term recurrence intervals, may need to be accelerated. Emergency drills based on specific warning scenarios may need to be broadened to include cases where the only signal is a subtle GPS nudge or an anomalous data blip. Education campaigns will need to bridge the gap between what people expect from an earthquake, loud, sudden, ground shaking, and what the fault may actually deliver, a slow, quiet build toward a final and terrifying crescendo. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the Cascadia slip? Do you think a major quake is coming? We want to hear from you. Thank you for watching, and see you next time.